It's your boy Zhang. Welcome to Physics 101.
Yo, and I'm Jay Swiss. Today we're here to talk to you about our new latest invention, the Mousetrap Car Mobile, aka Dark Matter.
So for some of our initial data collected, we have the mass of our car, which was 0.0937 kilograms. The length of our car was 0.402 meters. The total distance it traveled to when it stopped was 5.8 meters, and it traveled that distance in 5.36 seconds.
So the basis for our mousetrap car design was we took a cardboard plank, essentially, and we attached the mousetrap, we glued the mousetrap on top of the plank. So after cutting the rounded part of the arm that would usually be used to kill the mouse, we instead only took one of the arms and we extended that using a rod made out of Legos so it could be flexible so it wouldn't snap if too much force was applied. At the end of the rod was attached a fishing line which ran all the way back to the back axle. And as far as the wheels, we used CDs because we thought that the lesser amount of surface that touched the floor would create less friction and the energy would be maintained more efficiently as the car moved along the tracks. In the following video, you're going to see how our car functions. Our mousetrap car functions as many of the people's in the class does. It uses the spring on the mousetrap, and it uses this arm here that extends the end of the spring that usually comes over and would be used to kill the mouse. It takes this arm and it runs it much further than it usually would be able to. And at the end of the string, at the end of the arm is attached the fishing line. The fishing line runs all the way back past the arm into the axle. And so when the mousetrap, when you bring the arm back,
Here, look, we can show it.
the axle is.
When you bring the this arm back, you would tie this string to the axle, the axle that's attaching the back wheels to the cart. I don't have enough hands to do it, but as you pull it back, you'd have even more length of the string to wound up the car, and then that way it elastic potential energy is stored in the axle. And then when it's released, this thing snaps forward, and the fishing line pulls. Oh my goodness. It pulls the axle forward and propels the wheels to move, which is how the mouse car moves forward. So our average velocity that the car traveled throughout its course up until it stopped moving was 1.082 meters per second. That accounts for when the time in the beginning when it's accelerating and as well as when it's decelerating before it stops. The formula for velocity is distance divided by time, and basically we calculated this through measurements. We got the distance to be 5.8 meters, the total distance traveled, and the time it took for him to travel that much was 5.36 seconds. So we simply divided the distance divided by time to get 1.082.
The following is a video of our car accelerating from 1 meter to 2 meters.
Oh! Yeah.
Now here's the same video, except played in slow motion so you can better see how our car operates. The following is the position graph of our car based on the video you just saw. So from the position time graph of the mousetrap car from the video, which we obtained using Logger Pro, you can clearly see that as time increased, the distance from the original point of origin, which would be the 1 meter mark, was increasing. Although it is not easily visible by the human eye, the graph does exhibit a form of a parabolic curve, indicating that the velocity would be changing. But because the video was recorded at such a short time span, and the car only accelerates really from 0 to full speed in a short distance, almost before it even reached the 1 meter mark, you can not really see, unfortunately, the great curve or change in velocity.
The purpose of calculating our initial velocity was so that we could determine what the acceleration of the cart was as you see it in the video. So our initial velocity was calculated by using the formula distance divided by time, and the distance it traveled when it first enters or as it first passes the 1 meter mark in the time frame of 0.135 seconds is 0.144 meters. So you would simply divide the distance by the time, so 0.144 over 0.135 to get that its initial velocity was 1.067 meters per second.
So the next step in calculating the acceleration of the mousetrap car from 1 meter to 2 meters would be to find the final velocity of the car, which would be the point where it reached the 2 meter mark. So in order to do this, the exact same process is used as to find the initial velocity, except at this point, of course, the distance would be greater because it's further away from the origin, and the time would be also increased. In theory, because the car is accelerating, this velocity would be greater than the initial velocity, which is shown because the final velocity was 1.163 meters per second.
So here's our velocity graph of our mousetrap car, and as you can see, it has a positive slope, indicating that the acceleration of our car was also positive. So it was speeding up as time went on. You can see our 2 points graphed were the initial velocities and the final velocity. So as it traveled between the distance of 1 meter and 2 meters, it increased in speed and experienced an acceleration.
So now knowing the final and initial velocities of our car, with the initial velocity being at the 1 meter mark and the final velocity being at the 2 meter mark, we are now able to calculate acceleration, which is change in velocity over time. So we found the change in velocity was found by subtracting the final velocity minus the initial velocity, which gave us a change in velocity of 0.096 meters per second, and the change in time was 0.8 seconds. So knowing these two values, we were able to find the acceleration of the car by dividing the change in velocity by the time which it occurred over, and we calculated this to be 0.12 meters per second squared.
So this is the acceleration graph of our car, of our mousetrap car, and as you can see, the acceleration remained constant at 0.12 meters per second squared. This was due to the fact that we only obtained 2 points from which we were calculating the acceleration for, which was the initial velocity and the final velocity. And since those 2 points created a positive slope, our acceleration would be on the positive side.
So here's the energy bar diagram for our mousetrap car, including not only the video clip, but the entire motion of the vehicle from its rest point at 0 meters to its end point at 5.8 meters. So because this car was initially at rest, and the zero reference point would be the floor, the car had zero potential energy to start off with. So in order to get the car to move, we would have to put energy into the system through work by doing work on the car. And the way we do this is by coiling the mousetrap, by pulling the arm back and winding up the axle, which therefore which yields potential elastic energy in a great amount because the spring is pretty hard to pull back. So now that the car has lots of potential energy, when we release it, this potential energy is turned into kinetic energy over time as the car begins to move further and further forward and the potential energy is lost and transferred into kinetic energy. Now the reason the car stops is because there's friction involved which is applied through the axle and through the tires hitting the ground. So because work is done on the system, through friction, heat energy is lost. Therefore, the total mechanical energy of the system would decrease until it reaches zero, which is where the car stopped at 5.8 meters.
So the next thing we can talk about is incorporating Newton's 3 laws of motion. and applying them to how our mousetrap car works. The first law states that an object at rest will stay at rest unless acted upon by an outside force, and we see this as the mousetrap spring provided an outside force that launched the mouse car into motion. So as the spring was released, it caused an unbalanced force that created a positive net force, which allows the car to move forward from its resting point. The second law states that the formula F equals ma, which is force equals mass times acceleration, basically means that the more massive an object is, the more mass it has, the more force it will take to accelerate it. So basically, first we can calculate the actual net force required, which is mass times acceleration. So 0.0937 times 0.12, which got us 0.01124 newtons. So that's our positive net force acting on the car. And since this mousetrap you may think that's a small force, but it's because our mousetrap car is so light, and so the force necessary to move it is not very much. But if we were to move a real life car, the amount of force necessary would be much greater, which is why a combustion engine requires gasoline to convert chemical energy to mechanical energy. Lastly, our third law states that every action has an equal and opposite reaction. So as the spring snaps forward, it causes a fishing line to pull backwards and pull on the axles as it stretched from its wound up position to make the mousetrap car move.
Another aspect of the car that we would like to investigate will be the impulse and momentum of the vehicle based off of the brief clip shown of the car moving from the 1 meter mark to the 2 meter mark. So we all know that impulse is mass times change in velocity, and implying that it occurs over time, and momentum is only for a certain point in time, being calculated with mass times times velocity only. So in this case, the impulse would be 0.0937 kilograms, which is the mass of the car, times 0.096, which was the change in velocity, which we use in the acceleration equation. And this yields a 0.009 kilogram meters per second impulse. Now for momentum, we use the velocity at the 2 meter mark, or when the car crossed the 2 meter mark, which was 1.163. Now we accidentally used 0.096 as our mass rather than 0.0937. Had we used 0.0937, we would have multiplied that by 1.163, and that would have given us 0.10897 kilogram meters per second for the momentum. The data shown on the screen currently is inaccurate, but it is relatively close to the actual momentum of the car at that point.
So we were unable to calculate a numerical value for power since since power is work divided by time, and we cannot determine exactly what work was because of the fact that work would require us to know what potential energy is or elastic potential energy is, and the formula for that requires a knowledge of the spring constant, which is different for every spring that you use. In our case, it was the mousetrap car, and it just couldn't be determined from the information that we had. But we can still interpret its meaning in the mousetrap car. So work divided by time would mean the force times delta x, which was how far it went, which was 5.8 meters, divided by the time it took, which was 5.36 seconds. So the power, in fact, could be calculated if we knew the spring constant.
Upon calculating many of the physics-related equations involving a mousetrap car, we had a few questions for further investigation over the efficiency and different aspects of the car that could be changed that would increase distance and reduce the amount of energy lost through heat through friction. So the first question we had was, how would adding gears affect the efficiency of our mousetrap car? Now to answer this question, we would most likely go about it by instead of attaching the fishing line to the axle which directly turns the car, we would attach the fishing line to a different axle with a large gear on it, and that gear would be attached to a smaller gear which would actually turn the wheels of the car. So by doing this, we believe we would increase the efficiency of the car because the larger gear would be spinning because of the the arm pulling the string and therefore rotating the axle. And as this larger gear spins, it has an increased linear velocity on its edge. So in order for these gears to be meshed, the linear velocity of the smaller gear would have to match linear velocity of the larger gear. And if the linear velocity of the smaller gear matches the one of the larger gear, then its angular velocity would increase, and therefore the axle that actually turns the wheels would spin faster, and in theory it would transport the car further than we would as when the string was attached to the axle which controlled the car. Second question we had for further investigation was how would the extending of the arm of the mousetrap car affects the distance the car travels. We noticed that some of the groups who performed better in our class had larger vehicles that had larger arms. We believe that because the distance from the end of the arm back to the back axle would be increased, that means that the amount of times that the string could be wound around the axle would be increased, and which in turn would lead to a greater amount of rotations of the back wheels, which would therefore increase the distance that the car traveled. So in order to answer the question, we would most likely modify our vehicle and create a larger extended arm. If we did this, the result would most likely be that our car would travel further, and the amount of force, the arm would not swing as far because its linear velocity would increase on the tips, but its angular velocity would still be the same. So because its linear velocity was increasing, that means that the wheels would be pulled at a faster rate and it would also be pulled further. The last question we had would be, in what ways could you reduce the friction loss of heat? So we noticed that in our car, the car was unable to continue on to infinity because of friction taking energy out of the system, which with the system being the mousetrap, or with the mousetrap and the vehicle. So in order to reduce friction, we would want to possibly apply lubricant to the axle houses, which would allow the axles to turn more efficiently and lose less energy to heat, because the energy lost through heat is the energy taken out of the system, which causes the car to stop. Therefore, by reducing the amount of friction with the axles, we would be able to propel our car much further because the car would be much more efficient. This has been Physics 101 by your boy Jay Swizz and Jay Roan. Thank you for watching, and I hope this video was very informative.